Have you ever looked up at the night sky? Away from the bright lights of our cities, the view can be truly breathtaking. Thousands of tiny, glittering points of light are scattered across a vast, dark canvas. For as long as humans have walked the earth, we have stared up at this incredible spectacle. We have felt a deep sense of wonder and curiosity. We are a species that asks questions, and the night sky presents us with the biggest questions of all. Who are we? Where are we? And are we alone in this immense darkness? The stars seem to hold the answers, whispering secrets across unimaginable distances. Our ancestors saw more than just random dots of light. They saw patterns. They connected the stars to create pictures, telling stories of gods, heroes, and mythical beasts. These constellations became their maps, their calendars, and their storybooks. They used the predictable movements of the sun, moon, and planets to mark the changing seasons, to know when to plant crops and when to harvest. The universe to them was a grand celestial clockwork. Fast forward to today, and our view of the universe has been completely revolutionized. We no longer see the sky with just our eyes or simple telescopes. We have giant observatories on remote mountaintops and powerful space telescopes orbiting high above our atmosphere. These incredible machines can see across billions of light years. What they show us is a universe that is anything but smooth and uniform. Instead, it is magnificently, wonderfully lumpy. Imagine you are flying over a perfectly flat, endless desert. That would be a smooth universe, but the real universe is more like flying over the Earth. In space, the continents and mountains are made of galaxies. Our own Milky Way is just one of these galaxies, a swirling city of hundreds of billions of stars. This stunning structure became known as the cosmic web. It was as if the universe had a skeleton, and the galaxies were the glowing lights that decorated it. To answer this, we need to travel back in time. We need to go back to the Big Bang, the moment our universe burst into existence some 13.8 billion years ago. Our best theories tell us that in its earliest moments, the universe was an incredibly hot, dense, and energetic soup of particles and radiation. The fact that we are here, on a rocky planet orbiting a star in a vast galaxy, is the ultimate proof that the universe is not smooth. Our very existence is a testament to the universe's lumpiness. This ancient light from the infant universe is still all around us today. It fills every cubic centimeter of space. This relic radiation is called the cosmic microwave background, or CMB for short. In 1965, two American radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna in New Jersey. They had accidentally stumbled upon the afterglow of creation itself. These stunning new maps allowed us to measure the properties of the early universe with incredible precision. They revealed a map covered in tiny hot and cold spots. These were the primordial fluctuations, the seeds of all cosmic structure. One of the most fascinating ways to think about these patterns is not as pictures, but as sound. The primordial soup of the early universe was so dense that pressure waves, which are essentially sound waves, could travel through it. Before recombination, the universe was a battleground between two opposing forces. Gravity was trying to compress the denser regions of the plasma, but as the plasma was squeezed, it heated up, increasing its outward pressure. By studying the patterns in the CMB, we are essentially doing cosmic archaeology, listening to the faint echoes of the sound of the Big Bang. This graph is one of the most important plots in all of cosmology. It shows the strength of temperature fluctuations at different angular scales. It is the unique fingerprint of our universe. The data tells us that the universe is made of about 5% normal matter, about 27% dark matter, and about 68% dark energy. The agreement is so good that we can pin down the universe's age to 13.77 billion years. All this knowledge is extracted from tiny temperature fluctuations. But this incredible success comes with a very subtle and profound problem. The problem is this: we only have one sky to look at. Think about a scientist on Earth studying a forest to understand how all forests grow. They could study thousands of different forests across the globe, averaging out local peculiarities to discover general rules. We want to understand the rules that govern the entire universe. But we cannot travel to another universe to see if it looks the same. We are stuck in this one. Cosmic variance is essentially a measure of the cosmic uncertainty that arises from our limited viewpoint. It quantifies the idea that the specific pattern of structures we see might not be perfectly representative of the average universe. Imagine you could only ever study a single acre of forest. If that particular acre happened to contain an unusual number of very tall trees just by chance, your conclusions would be skewed by local, random variations. When we look at the very largest features on the sky, there are only a few of these gigantic waves visible on our map of the CMB. When you only have 2 or 3 examples of something, you just cannot get a very good statistical average. Imagine we could magically transport ourselves to a galaxy billions of light years away, in a completely different part of the universe. Let's call it Galaxy X. According to our standard cosmological model, the new map would look statistically identical to our own. However, the specific pattern of the hot and cold spots would be completely different. Each observable universe is just one random draw from an enormous bag of possibilities. Our universe is not special, but it is specific. Cosmic variance acts as a final, unbreachable frontier in our exploration of the universe. The uncertainty that comes from cosmic variance is different. No matter how perfect our telescope is, we cannot make this particular type of uncertainty go away. When we look at the largest scales of the CMB, cosmic variance dominates our error bars. This means our measurements of the universe's properties at these scales will always be fuzzy. Ultimately, cosmic variance is a lesson in cosmic humility. It reminds us that we are part of the universe we are trying to study, not separate from it. Our journey has taken us from the familiar patterns of the night sky to the very edge of observable reality. We began with a simple question: why isn't the universe smooth? The cosmos we inhabit today is the result of tiny, random imperfections present at the very beginning. These minuscule fluctuations were the seeds of everything. This lumpiness is not just an interesting detail for astronomers to study. It is the single most important reason we are here to ask these questions in the first place. Every atom in our bodies, forged in the heart of a long-dead star, owes its journey to us, to those primordial ripples. We are the children of anisotropy. The great cosmic web is not just a map of matter, it is the story of our own cosmic ancestry. It shows how gravity worked on the raw material of the Big Bang for billions of years. The imperfections are not a mistake. They are the essential ingredient that makes the universe come alive. The secret of the universe is that its beauty and its potential for life are born not from perfection, but from a tiny, essential, and magnificent imperfection. This realization leads us to one of the deepest questions in all of science and philosophy. If our existence depends so critically on these primordial lumps, does that mean the universe was somehow designed for us? Our universe seems to walk a knife edge of possibility. This is often called the fine-tuning problem. Many fundamental constants of nature seem to be precisely dialed in to the values needed for a complex, life-permitting universe to exist. One such idea is the multiverse. Perhaps there are countless other universes, each born with slightly different laws of physics and different initial conditions. While we have pieced together a remarkably complete story of our universe, the journey of discovery is far from over. Future telescopes and experiments are being designed to tackle these very questions. The quest to understand the lumpy universe is now a quest to understand its dark side. Deep underground, hypersensitive detectors are searching for the faint signal of a dark matter particle. But as a species born of curiosity, driven to explore and understand, there could be no greater adventure. The story of the lumpy universe is the story of us,